Hello, Shine sir. Shall we proceed?
Yeah, we can start, sir.
Okay.
So, good afternoon, everybody. In this session, we are very fortunate to have an eminent speaker, Dr. Sony Varghees, Associate Professor, Department of Chemistry, NIT Calicut. He did his PhD from Eindhoven University of Technology, Netherlands, and his area of expertise are nanomaterials and devices, nanofabrication, liquid crystal display, polymer technology, MEMS, etc. And he has many international journals to his credit, and he is also the in charge of Nano and Display Research Laboratory, School of Nanoscience and Technology, NIT Calicut. On behalf of MES College of Engineering and the coordinators of FDP, we invite you, sir. Please.
Thank you very much. Good afternoon, everybody. So thank you, the coordinators, Dr. Sunesh and associate coordinators for inviting me for this session. So let me share my slides and I'll switch off my camera.
Can you see my slides, please?
Yes, sir. Then go to presentation mode.
Yeah, sure.
Slideshow.
Can you see it properly?
Okay, sir.
All right. So good afternoon once again. So today's talk, I would like to discuss some aspects of
So I think your voice is low.
just a minute, sir. Sir, how is it now? Is it better?
Yeah.
Okay. So today's talk, we will basically looking for advances in liquid crystal display. So when the coordinators asked me, so I was just thinking something to connected to optics. So I thought liquid crystal display, anyway, it's highly optical devices. So I thought I'll just discuss something on liquid crystal display devices. So basically, we will start with some fundamental aspects of display devices, then a little bit on latest advances. If time permits, we can also I can also discuss something on our research activities on display devices, right? So as you know, LCD devices or liquid crystal display devices are becoming one of the very important human machine interface, right? Devices, right? So especially once the online classes started, you have seen that the importance of such type of devices, display devices. So the teachers and everybody are using most of these information display facilities to have classes online. So especially during this pandemic period, you have seen that the importance of this type of display, right? And moreover that we are well used or are very well using this type of display devices, starting from our mobile phones to laptops or big screens or other devices, right? So a lot of history is there for this type of display devices, right? So there's a huge market. There's a huge market for this type of display devices. And if you go to the consumer electronics, right, you can see that most of these are literally very fancy items and which are very useful nowadays, right? So it's highly if you look at the customer point of view, this type of display devices are finding a huge market, right? And if you look different type of display devices, so we used to call it as information display devices, right? Information display. So whatever the information is displayed, such devices we call it as information display devices. And you can see that there are a variety of display devices are available. So starting from your conventional cathode ray tube, from that you can see that we have started already the flat panel displays. Now you can see that no more we are using this bulky conventional cathode ray tubes. We are not at all using. I think most of the companies have shut down the manufacturing plants and they have completely moved to the new display devices, right? And moreover, we have plasma systems are also available, and we can see that we have inorganic or organic or LEDs based on OLEDs or PLEDs are also available. Most of your mobile phones may be AM LED or LED actiometrics organic light emitting diodes, right? Or we can also think about electrophoretic displays like Kindle reading boards, etc. Then you can see about this field emission displays. So there are a lot of displays nowadays. You can see that the emergence of such type of displays we can see nowadays, right? But if you look among these displays, you can see that still the liquid crystal displays are widely used, right? So a lot of changes are happening nowadays. A lot of improvements are taking place with respect to this conventional systems, right? So if you remember our simplest calculators, which is available long back, right? The same 7-segment small display devices. So that I would say that was a starting point for this LCDs. From there onwards, we have started with uh, the field effect transistors, field effect transistor having LCDs, FET LCDs, right? Then you can see that there is further improvement in this area. So we have seen the introduction of quantum dots LCDs displays, right? So widely used nowadays, and there are a lot of improvements you can see with respect to this LCD systems, right? And as I told you, we are almost completely out of this bulky CRTs. Nobody is using nowadays. Only we are going for flat panel displays, right? Because a lot of convenience are there with respect to the power consumption or portability or aesthetic appearance, etc. So there are a lot of advantages are there with this machines, right, or these display devices, right? And you can see that this is the period where the CRTs were started replacing. I think during this period, 2010, 1995 to 2010, and you can see that we have started devices for different human machine interfaces, including mobile phones or televisions. And you can see that in 2015 or onwards, we can see more on smart, flexible devices. Then you have smart televisions, etc., were introduced during this period. So a lot of improvement, a lot of integration is happening based on this LCD devices, right? And if you look at, you can see a little bit on the what is happening nowadays. You can see that this is the projected development of the flat panel display market by the display type. So you can see that we have flexible displays devices. I think recently they were introduced. Then we have a flat panel that is actually introduced long back with the transparent and non-flexible systems, right? Just a minute. So we have, am I audible, sir?
Yes, sir, you are audible.
Okay. Yeah, if you look at the flat panel market, we can see that this is the amount on the y-axis that is in $1 billion. We can see this is the huge market for this flat panel display, right? And if you look at different aspects, nowadays we have the 3D televisions, high K, 4K, 8K, 16K, different type of display devices are introduced, right? Smart televisions are introduced nowadays. So there are a lot of integration or research going on this area. So display devices is one of the unavoidable part of our room, right, or the living room, right? And you can see that if you look at the cost of the display day by day, also if you look at the cost, you can see that day by day the cost is also decreasing, right? And if you look at the distribution of cost among the different parts of a display systems, we can see that around 2 to 3% of the cost is coming from the liquid crystal materials, right? Liquid crystal materials and other contributions. You can see the backlighting systems. It's also very contributing than other devices. So this is if you look at the display devices, right? So I can say that that's a very beautiful engineering marvel, right? Because you can see that starting from different type of materials like liquid crystals, right, to the complex electronics using this field effect transistors, right? Then coming to the optics, complex optic systems are also there. So it's a if you look at the overall display unit, we can see that if you look at the research areas, it's highly interdisciplinary area, right? So people are working on optics to improve the performance. For example, if you want to make a perfectly black system, usually the problem with liquid crystal is that the materials are anisotropic, right? And because of that, there is light leakage, and that will make films based on the application or use of LCD. You can see that 2010, the area of LCD panels. I'm talking about the LCD panel area, right? And you can see that in 2010, the area was around 113 kilometer square, right? And you can see that in 2017, it became 179. Probably it has reached more than 200 nowadays in 2021. Definitely, just area. Just imagine how many display devices are a single person is using. If he is using a 50-inch television at his home, right? With a 15-inch laptop, with a 10-inch mobile phone. You can see that you can just calculate the area per person who is using. So it's a huge demand for such type of flat panel displays, right? And you can see that this is just showing you the area. For example, 36-inch display device, and if you want to increase the size by 1 inch, so you have to add 6% more liquid crystal materials, right? So, nowadays, we can most of very huge size display devices are available, right, in the market, and also the price is every day it's going down, right? And we can see that the switching characteristics, as I told you, we call it as the display response time. And 2015, it was 15 milliseconds. Now we can see that it is around 1 milliseconds, right? So there's a huge difference in the switching time also, or the response time of the material. And you can see that this LED backlighting, and for 2005, we are using 15 centimeter length backlighting, and nowadays you can see it's only 0.8 centimeter LCDs for the backlighting, right? Or the thickness of the display, because that the backlighting, they have changed from a conventional systems. They are using cold fluorescent lamps. Now what they have done is they have replaced with LEDs, right, as a backlight. So the thickness, the display thickness has considerably reduced, right? You can think about your laptop screen. If you take a mobile phone, you can see how they are reducing the thickness, right? So all these are actually customer requirement. So customer need very thin displays, right? They need a high fast responding displays, right? So a lot of requirements from the customer side leads to the improvement of this type of display systems. And this is this display diameter. You can see people are thinking about. You can see that nowadays we have 110 inch or bigger than that. And if you look at the contrast ratio, as I told you, it started from 1:1000, right? So the contrast ratio is nothing but the ratio between the bright state and the dark state, right? And that is in the white screen and the dark screen. What is the ratio of the light intensity, right? So earlier it was around 1:1000. Now you can see that it can go more than 10,000, the contrast ratio. So higher the contrast ratio, you can expect beautiful images, right? And there are a lot of improvement on the material aspects to improve the contrast ratio, right? So nowadays, I think what we are getting nowadays, even it can go around 1 lakh contrast ratio. So the huge difference in contrast ratio leads to beautiful, vivid, lively images, right? So you can see, and also the pixels, number of pixels per inch. So we call it as PPI, pixels per inch. So you can see the full HD televisions. You can see this is the pixel. What we usually around 13 pixels per inch, and you can see that for ultra high definitions, it has gone to 52 pixels per inch. That means the pixel size has reduced, right? The pixel size has reduced. The smaller the pixel, higher the clarity, because your eye will not be able to detect, because it is beyond the resolution of your eye, right? So your eye cannot resolve the pixels, and you will see it as a single image, right? So the importance of this PPI, that is also increasing, right? So you can see nowadays it's more than 52 pixels per inch. And surface area, I already told you, we have a huge requirement for the flat panel displays. And and if you look at the cost also, you can see that it is around $5 per square inch, right? And for the OLED based TVs, whereas for LCD based TVs, you can see that it's only $1 per square inch. So I think the cost is also reducing. considerably, right? And you can see that there is a competition between OLED-based display devices and LCD-based display devices. Even though OLED-based display devices can give you better images, but if you look at the cost-wise, they were actually on the higher side, right? But you can expect very high contrast images when you use OLED-based display devices. But if you look at the longevity also, I would say LCDs are having more life compared to OLED, because OLED, basically they are using organic molecules, and there are chances that the molecule may degrade for long run, right? So in such cases, maybe some, if you look at the life, probably LCD may have better life than OLED, but definitely if you look at the quality of images, OLED are always superior, right? So there is no doubt about that. And you can see this is the display industry forecast by annual production capacities. You see that displays square area, and you can see that the LCDs are still on the higher side. OLEDs are even though coming. Plasma is also there, but they are very, very expensive. One of the affordable display device which is available currently is only LCDs, right? If you look at the other OLED-based, I think consumer market is still has to come. The OLEDs are not available for huge or large area displays. OLEDs are now available only for small display devices like mobile phones or tablets or something like that. We can have these OLEDs, but LCD is expecting a huge amount. The price will increase when we go for these OLED-based display systems, right? So this is just a comparison of the LCD market nowadays. You can see that in most of the cases, we can see that LCD is actually still on the higher side, as I told you, because of the low price of this such devices, right? So coming to a little bit the basics aspects of this display, if you are not already familiar, please excuse me. Otherwise, I'll just give you a brief idea about the different operating aspects of LCD devices. Then only we'll go to a little bit on current advances, right, on this display systems. So basically, we can divide LCDs based on the type of operations we are implementing, right? For example, we have a twisted pneumatic LCDs, right? Twisted pneumatic LCDs. Actually, these are actually used in old watches, calculators, etc. Nowadays, we are not using it for display, but only for still we are using it for watches or calculators. Still, we are using this twisted pneumatic LCDs, right? Then we have a super twisted pneumatic LCDs, which is also used in personal organizers, watches, or calculators, etc. And we have these third and fourth, that is in plane switching, as well as vertically aligned LCDs. So I would say these two are the most important display devices which are commonly used in flat panel displays, right? So we call it as IPS. IPS stands for in-plane switching, right? Probably in some advertisement you will see that in-plane switching, right? So I'll come to that. So most of the flat panel displays are based on this in-plane or vertically aligned mode, right? And I'm just comparing different type of displays, different devices here. You can see most of the cases, as I told you, for flat panel displays, we are commonly used IPS mode of switching, as well as vertically aligned mode, right? Then other things are used for small gadgets like calculators or small display devices, right? And you can see that for different type of display systems, we are using different materials. So what you are seeing on the right side, different chemical molecules, which are known as liquid crystal materials, right? So you can see this is the 1888. That was a starting point where Frederick Reitzner of University of Austria, right? So he has developed this cholesterol benzoate. So this material is cholesterol benzoate. So this is the first liquid crystal molecule actually reported in 1888. From there, you can see that in 1972, there are some devices which uses this type of molecules. So these are called cyanobiphenyls. Then later you can see that there are a lot of improvements. And nowadays we are using fluorinated liquid crystal molecules that is actually used in most of our display devices, right? And if you look at the cross section, or if you just open our liquid crystal molecule, liquid crystal display device, you can just watch this movie. I hope you can see the video. Can you see the video playing?
Yes, sir.
Okay. Yeah, we are just zooming on the screen, right? So you can start seeing the pixels. As you know, the pixels are the picture elements, which contains the primary colors, red, green, and blue. Each pixels contains three colors, subpixels, red, green, and blue as primary colors. So, and we have individual control on each pixels. We can play with each colors by just changing the voltage applied to the transistor on the subpixel, right? So the transistor, the field effect transistor is a switch which is used to switch each subpixels. So each pixel will have a transistor. Okay, so you can just watch this video. So I'm just focusing on a single pixel, right? So this is a single pixel. And if you look at the cross section of this pixel, so it will be like this. Yeah. So the cross section will be something like this. So you can see these three colors, red, green, and blue. And each pixel, you can see some sort of a twisted structure. So that is nothing but the liquid crystal molecules, right? So if you look at the structure, it will looks like this, right? It will looks like this. So you have the red, green, and blue pixels. So so actually these are called the color filters. We have color filters. So I'll start from the back side. So you can see that the back side we have a source of light. So you can see that unpolarized white light, right? So this is the unpolarized light. So we have a polarizer. Next to that, we have a polarizer. So the polarizer will polarize the unpolarized light to plain polarized light. So then after that, you have a glass substrate, right, on which we have a transparent electrode, right? So that is called indium tin oxide. Indium tin oxide is a transparent conductive electrode that is coated on a glass substrate. And on the glass substrate, we have ITO, indium tin oxide. And on that, we have another one that is called the orientation film. So that is actually responsible for the orientation of these molecules or the liquid crystal molecules. The details, I'll come to that. Then in between and after that, you have a thin layer of this liquid, right? So which is called a liquid crystal, right? I think when you touch on your laptop screen, probably you have seen some liquid moving, right? So that is because this liquid is present here, right, as a sandwich structure. So you can see that the same thing is repeated in the bottom side. We have an orientation film followed by indium tin oxide transparent conductive electrode, then a glass substrate, then a color filter, again a polarizer, right? So this is the structure. So basically, we are using unpolarized light. So the source, as I told you, nowadays we are using LEDs, light emitting diodes are used as a source, right? So because of that, we used to say LED display. Actually, it is not LED display. Only the backlight, right? Only the backlight is an LED. So it is actually an LED LCD display, right? LED LCD display, right? So people will be confused. So when you go to the shop also, they will say that, yeah, you can buy an LED display. No, nobody will tell that LCD display, right? Because what LED means, it's only the backlight. But Pure LED displays are also there, as I told you. These are not yet on the market. Expecting very soon, completely, but they are very expensive. But a normal display, if you normal televisions, if you buy, it will be an LED LCD display. So LED is only the backlight, right? That is source of light. And if, in a nutshell, I can say that LCD's pixel, if you just take a one pixel, which contains 3 subpixels, right? I can say that it is actually a light valve, right? Each pixel is a light valve, or a subpixel is a light valve. It is actually controlling the light which is coming from the backside, something like a tap, right? So when you open the tap, you will get water. When you close it, the water is stopped, right? Similarly, the liquid crystal material is acting as a valve here, right? So you have the backlight is there. Light is already in the back. When you switch on your laptop, light is on from the back side, right? But the light which has to come towards you is controlled by this liquid crystal material, right? So that light is actually coming through a colors. Then you are getting the colors. So when you apply electric field, you can control the alignment of these molecules, and by which you can control the light transmission, right? So that is what actually happening here. So I'll just to show you another video. Let's see this one. I hope you can see this. Just a minute, I think. Just to play again.
This monitor uses liquid crystals to display images. How this thing works amazes me. Let me show you. Let's start at the back of the screen. If you look here, you'll see a row of LED lights at the bottom called the backlight. These are the only lights in the monitor. Next, I'll put in what's called the optical system, which makes the light even across the back of the screen. Now, the first sheet makes a nice, even white background for the light. The next piece is called a light guide plate. You can see it's covered with dots. When light enters from the bottom edge, it propagates down the plate by total internal reflection, unless it hits one of the dots. And they make some of the light rays emerge out of the front. Then engineers place a diffuser film. It helps eliminate the dot pattern from the light guide plate. Then comes a prism film. You can notice here that where I have the sheet, it's much brighter than where it isn't. So at this point, if we put the last diffuser film on, we have a very evenly lit surface, all from a single row of LED lights at the bottom. The backlights are always on, but what controls what we see is this piece of glass. It functions as a shutter. At the back and front of the sheet are 2 polarizers. They stick tightly to the piece of glass, but let me illustrate it with 2 sheets that I have. If I lay this sheet on the optical system, you can see that it passes light. And if I put this piece on top, it also allows light to pass. But if I rotate it exactly 90 degrees to the bottom sheet, you'll see the light disappears. The bottom sheet creates polarized light, which will only pass through another polarizer set to the right angle. Now, of course, in this LCD monitor, the front polarizer doesn't rotate. Other than the on-off switch, the monitor has no moving parts. Instead, what we do is we place these 2 polarizers 90 degrees to each other, this configuration that allows no light through. And then, if we want light to pass, we twist the light within the glass pane to match the front polarizer. How? Well, it's a simple-looking piece of glass that does all the magic. Let me put it back on, and you can see that the image reappears. I just love that. It's actually a sandwich of glass. Engineers fill the space between the panes with tiny glass beads to keep them separated, and with organic molecules known as liquid crystals. The crystals have interesting properties in that they do not allow light to pass uniformly along both axes. Grooves are formed on the surface of both pieces of glass at 90 degrees to each other. The molecules in between line up in a beautiful helix. When light from the backlight passes through the first polarizer and enters the sandwich, it's rotated by the liquid crystal so as to allow it to pass through the second polarizer and emerge out the front of the screen. This is known as the normally white mode. Applying an electric field across the sandwich causes the crystals to line up lengthwise. Now, the light that passes through the front polarizer is not rotated by the crystals and can no longer pass through the front of the screen. We call this the normally black mode. Now that we can control the light through the glass, how do we get color? Let's look in detail at the piece of glass. By controlling the voltage between these transparent electrodes, we can control the intensity of the light that passes through. Now, there's much more to the glass plate. Let's examine this section where my sleeve meets the gold background. If we zoom in, you can see it's made of pixels. If I turn off the image and backlight the glass sandwich, you can see the screen contains red, green, and blue sections. These are subpixels. The three together make a single pixel. In the sandwich, they are simply colored tiles that overlay the front transparent electrodes. They follow the RGB color model. We adjust the electrode shutter behind the subpixel so that they make up a particular color. For example, to get the color of the blue in my shirt, we set the red subpixel to 12% of maximum intensity, green to 21%, and blue to about 50%. And now for the last critical piece in the glass sandwich. On the back pane, engineers paint tiny devices called thin film transistors. That's why these monitors are often labeled TFT. Each subpixel has a transistor which controls it. This transistor you see here functions as a switch that allows the screen to be updated row by row. By applying a voltage to a specific row while keeping the other rows grounded, we allow each subpixel in that row to receive video data coming from the top of the screen. Only one row can receive information at a time, but the speed with which this happens for each row is so fast that your brain blends it into a fluid image. What an amazing device, and also the technology that allowed computing to go mobile. Imagine laptops, cell phones, and tablets without lightweight screens. I'm Bill Hammack.
I hope you got some aspects of the working of this system. Yeah, am I audible?
Yes, sir.
Okay. Yeah. Yeah, as you have seen in this previous video, we can see that this twisting, actually the twisting is one of the very important aspect of most of these display devices, right? So the interesting thing is that if you look at this molecule, and you can see that they have aligned in a helix like this, right? So actually this orientation or this twist is actually formed because of what you call the orientation films, which is on the top of this indium tin oxide, right? So you can see that this is the twist formation. So when you apply electric field, you can see that the twist is lost, and light can come out depending on the orientation of your second polarizer, right? So basically we are dealing with polarized light, and the polarized light will be guided by the column of liquid crystals, and they will be twisted 90 degree. So that's why it's called a twisted dematic. Then the second polarizer will block, right? And when you apply electric field, the twist will be lost and light start coming out, right? So that's where things works, right? So this is the alignment arrangement of this typical twisted dematic. So basically, twist is there. We can see that this is the twist, and when you apply electric field, the twist will be go and the light has to come out, right? And so this is for the super twisted. Super twisted means we can see that the twist angle will increase to 180 degree, right? You can see that in the previous case, the twisting was only 90-degree twist, right? But in this case, the twist will go to 180 degree. So that depends on the material which is used as liquid crystal, right? So certain materials can, if you add as a dopant, so we call it as chiral dopant, they can increase the twist sense, and by which you can increase the twist. Increasing the twist actually increases the switching speed. So there are some devices which uses this STN, super twisted display, right? And for parallel aligning methods, and you can see that the molecules will align like this. You can see that they are aligning like this, and you will be applying electric field. Then you can introduce twist by electric field, just opposite of what you have seen in the previous cases, right? And for in-plane switching, you can see that. So this is the in-plane switching. In this case, you can see that the electrode is present, especially on the bottom side, and electrodes are like this. So you have the pixel like this, and the molecules will be rotating on the plane of the substrate or the glass. So that's why it's called in-plane. So most of our commercially available televisions are based on this in-plane switching, right? So light will be coming from the bottom, and when you apply electric field, the twist will be lost, then the light will come out, right? Depending on the orientation of the analyzer or the second polarizer. Okay, and so this is actually the in-plane switching. So you have the electrode on the bottom substrate only, and you can see that there is already a twist. And when you apply electric field on the bottom, the twist will be lost and light start coming out. Okay. And for vertical alignment, and you can see this, this is the configuration. The molecules will be aligning like this vertically, right? And when you apply electric field, and you can see that twist will be introduced and the light can come out because we are keeping the polarizer in a different manner, right? So that's how. So both this IPS as well as this vertically aligned modes are commonly used in display devices. Okay. And how will you make if you want to make in a lab, you can make small devices. So we do this type of research in our laboratory. We do work on how to improve the switching time, how to increase the switching time, sorry, decrease the switching time, right? Or improve the performance of the display with respect to the orientation of the liquid crystal molecules and different materials we are using. For example, we have this is how we start with. We'll be starting with indium tin oxide plates, and you have to coat with some alignment layers. Alignment layers, usually we use this, polyimide. So that will be spin coated like this, followed by curing process. Then you will be rubbing this polyimide film, right? Rubbing process, right? So rubbing process, actually what happen is that rubbing will be done on a velvet cloth, right? We are rubbing your substrate on a velvet cloth, and because the velvet cloth contains small fibers, so that will introduce some scar or scratch on this polyimide film, right? So small grooves will be formed, right? Then you will you will keep it like this. You will keep the uh, rubbing direction orthogonal to each other, right? 90-degree, right? So we will keep these two like this, and we will keep a spacer, right, around 5 micron spacer. So then you will put some glue. Then you will stick these two plates, right, with a 5 micron gap. Then by capillary action, you can fill the space using some liquid crystal molecules. Then the device will be ready like this. So this is just for research purpose only, not a actual display device for entertainment. Just for some simple LC or digital pneumatic display if you want to make. So you can do this like this. And if you put it on a polarizer, it will be like this in the middle. You can see that in a cross polarizer, the light is coming from the middle. Outside, you can see that black area. That is because it's a cross polarizer. So light will be blocked. But in the middle, you can see that since there is a twist in the liquid crystal molecules, light are coming out. Right. So when you apply electric field, you can see that just opposite takes place. Right. So the middle part, you can see that the light is blocked. The twist is lost, so light cannot come out. Right. So this is a typical display, a small display device we can make. Right. So this is the rubbing process we do. This is the polyimide film, which is rubbed using a rotating system, right? But of course, if you don't have this facility, but you just take a velvet cloth, then you can rub, you can control the alignment of these molecules. And you can see that this is what is called this Gooch-Tarry curve. Actually, this is actually telling you your transmittance of your display device with respect to the cell thickness. So as I told you in the previous case, the cells or the two glasses were glued with a spacing of 5 micron. So what is given in the x-axis is thickness of the spacing, right? you can see that this is given in 5 micron. You can see that if you decrease its thickness, you can see the transmission start increasing, right? So usually it is coming around less than 5 micron, around 4 or 3 micron, you will get a better transmittance. So this is based on this huge direct curve, right? Then if you just coming to the material side, as I told you, so this is Professor Frederick Reitzner from Prague, and he was an Austrian botanist who first developed or first found out this material, cholesterol benzoate, having a clearing temperature of 145 degree and a pneumatic transition temperature of 179 degree, right? So this is the first molecule which is derived, right? Later, 1971, there is some device, a simple device using this twisted displays, right? Then you can see that if you just look at the material side, especially the liquid crystal materials, right? We have different class of these materials. We can have a lyotropic or thermotropic, right? Thermotropic actually that depends on the temperature of the material, right? Temperature of the surroundings. The material property depends on the temperature. So in most of the display devices, we use thermotropic systems, right? So the as I told you, the molecule will looks like this. It's like a cyano biphenyl having a structure like this. So for a chemist point of view, the molecule will be like this: two phenyl group connecting like this with a cyano group and a alkyl group like this. And for a physicist or an engineer point of view, the molecule is having a rod shape, right? So we can consider we are looking at the shape of the molecule. It's having a rod shape, and it is called the shape anisotropic. So the length is greater than width. So the molecule is around 2 nanometer length with 0.5 nanometer width, right? So this is the molecule we are talking about. Okay, so we can have low molecular weight liquid crystals as well as high molecular weight liquid crystals. We call it as liquid crystal polymers, which are used in different applications, including high strength materials, right, etc. But in our case, we are looking for the low molecular weight materials. And if you look at the faces of these materials, you can see that. So this is a perfect crystal, right? This is a perfect crystal, and this is a liquid. So we can call it as isotropic, right? Isotropic. If you take water, which is isotropic, right? So there is no specific orientation. Molecules are randomly oriented. You don't have any orientation. But if you look at the liquid crystals, we can see that its orientation is something between crystal and a liquid, right? So it's something like this. So we call it as the pneumatic phase of the material, right? So our material is having this orientation, right? So we used to express in terms of order parameter. Order parameter is actually 1 for a crystal, whereas 0 for isotropic systems, right? So order parameter is 0 for isotropic and 1 for the crystal. And for the liquid crystal, the order parameter will vary from 0.3 to 0.8. So we can imagine some order which is present in the material, right? So I'm just showing you 3 class of material. You can see this is a crystal material, and you have isotropic, that is water or something like that, and this is a pneumatic, right? So so you can see that the liquid crystal is a liquid, but at the same time, it has some crystalline properties or properties of crystals, right? So you can see the color. The color is similar to a crystal. You can see that the cloudy nature, right? The cloudy nature shows that there is some crystal phase present because the light will come and scatter, light scattering, right? Because of the crystals present in this phase of this material. So this type of materials are actually used for display devices, right? Pneumatic crystals, right? And we have other phases also, spectric A, spectric C, etc. That depends on the orientation of this, what you call the directors or the molecules. So I'm not going to discuss that. And also we have polymer liquid crystals are also there. So that is, these are just large molecules which are connected to each other, forming high molecular weight materials, right? So that is also just giving an idea about this material, right? Then liquid crystal materials are actually sensitive to temperatures, right? So the temperature is very, very important, right? In ambient temperature, the material should be in the pneumatic phase, right? Then only your display will work, right? If you increase the temperature, or if you keep your mobile phone in an oven and just increase the temperature to some 60 or 70 degree, you can see that you can't see anything. Your display will not work, right? Or if you freeze your mobile phones to -20, then also your screen will not work. So the operating temperature, that will be usually mentioned by the manufacturer, right? So because the thing is that the material should have a pneumatic isotropic transition temperature. So the display system should work in that temperature range. Then only you can expect proper working of your system, right? So the temperature is also very important, right? And moreover, you can see that we have anisotropy, right? Anisotropy present on the material, right? If you look at the structure of this molecule, so we can see that one side you have some negative, or well, if you say on a chemist point of view, you can see that highly electronegative materials are groups are present. For example, cyano group. Cyano group is highly electronegative, so they will pull the electrons to the cyano side. So the opposite side we have a positive charge. On other side we have a negative charge. So there is a polarization of the molecule, right? So the material is highly polar, right? So that is the reason why the material will twist when you apply electric field, because the electric field interact with this polarization of the molecule, then the molecule start rotating, right? So that is the basic idea. So molecule should be polar, then only it will be twisted by the electric field when you apply, right? Then the wave guiding will be lost, the light will pass, right? So the polarization is very important, right? So we have a negative as well as positive anisotropic liquid crystals are available depending on the application. For example, if you are using in plane switching, in that case we are using a positive dielectric constant material, whereas for vertical alignment display we are using negative dielectric constant material. So that depends basically how the molecule is polarized, right? So this is actually a video, but unfortunately it's not working. So basically showing you the when you apply electric field, what happens to the liquid crystal molecules. So basically you can see that there is a polarization takes place. And also the surface is also very, very important. The orientation of these molecules depends on the surface, right? For example, a molecule can lay flat on the surface, so we call it as planar arrangement, or the molecules can stand up like this, so we call it as homeotropic alignment, right? Different type of alignments are there. For example, in plane switching we are using this planar alignment, but for vertical alignment we are using homeotropic alignment, right? So in that case we are using negative dielectric material, right? So this is surface anchoring. So we used to say the molecule will have some attraction to the surface. So that is what the surface anchoring means. And the molecule will also possesses some angle with the surface. We call it as pre-tilt angle, right? So these are some basic parameters we usually counted when it deals with such molecules. And if you look at the material side, especially the liquid crystal material for display applications, and we can see that liquid crystal property and liquid crystal display property. How the liquid crystal property connected to the display property, right? So that's what you can see here. For example, the liquid crystal clearing point, we call it as the pneumatic to isotropic transition temperature, and you can see that depends on the operating temperature range. So this is very important, because then only we can define your operating temperature. What is the temperature range in which your display device is going to operate or going to work, right? The melting point is also a parameter. Then birefringence, that is also, you can see that is connected to the brightness, the contrast ratio, as well as the viewing angle of your display. The birefringence is very important for this display systems. Then dielectric anisotropy, that is also connected to the brightness, also connected to the contrast ratio, the viewing angle, as well as the operating operation voltage, right? The dielectric anisotropy. Then the elastic constants of these materials, that also depends on the brightness, contrast ratio, viewing angle, operation voltage, as well as response time. So elastic constants is something to do with the viscosity of the system, because when you apply electric field, the molecule has to move, right? Molecule has to move, so that depends on interaction of the molecule with other molecule, viscosity, how fast it can move, because this is a thin film of material. When you apply electric field locally, that molecule has to twist or to move, how fast it can move. So these parameters are related to the elastic constants, right? Then the rotational viscosity of the material, that is also related to response time. So many parameters of liquid crystal is actually directly related to your display property. If the response time is less than when you watch a video, you can see that people are moving maybe in a slow motion, or you won't be able to see properly. There is always a delay because the molecule is not fast enough to move, right? So there are so many parameters, depends on how you have to choose a particular liquid crystal proper material for to attain a particular display property, right? So because of that, a single liquid crystal we cannot use, because it's very difficult to achieve the property, liquid crystal property as mentioned here. So we have to go for a mixture of liquid crystals, right? So usually, it's something like a perfume. If you take a perfume, you can see that it's not a single molecule. It contains multiple type of fragrance, right? I think at least 25, more than 20 different fragrance may be blended to form a perfume, right? So similarly, in this case, at least 6 to 8 or 10 different liquid crystal molecules will be mixed at different proportions to attain these display properties, right? So it's not a single molecule to be used, it's a mixture. And you can see this is how the structure, you can see the polar group, it's a bridge group, alkyl chain, right? And this is the basic structure of the molecule. These are some examples of the terminal groups used. These are some of the bridges used. I'm just going a little bit fast on this side. These are some common groups used in this type of displays. So these are some examples of some polar substituents. As I told you, nowadays, most of the liquid crystals we are using is fluorinated materials. Fluorinated. Fluorine is highly electronegative, and because of that, you have a very good polarization expected. So you can have a better switching if the molecule is more polar, right? So when you apply electric field, they will switch fast, right? And so this is just liquid crystal mixtures, as I told you. So we are dealing with the eutectic mixtures. So you will have to blend different materials. So a single substance will not be sufficient. So we have to make it as a mixture of different molecules. This is how the display industry. And you can see that this material is very expensive. I think there's only few companies which makes this type of materials. For example, German companies like Merck, they are manufacturing tons of liquid crystal for industrial uses, right? So it's a mixture, right? So these are some examples of molecules which are used as liquid crystals. As I told you, we are using fluorinated materials, liquid crystals, because of the good voltage holding ratio, high specific resistivity, high dielectric anisotropy. Then we have lower melting point. So many parameters are there, which can be met when you use fluorinated liquid crystals. So these are some examples of fluorinated materials, especially you can see that these materials, right? Then coming to some other developments in the LCD is this quantum dot displays, right? So nowadays, there are a lot of advertisement of coming from the quantum dot displays. I think if you visit some electronic shops to buy some display device, televisions or something like that. Probably you can see that the QLEDs. So they have written as QLEDs, quantum dot displays, right? But you can see the quality of these displays are amazing, right? And even Samsung, I think you can see the curved quantum dot displays. It's a curved type displays. But if you look at the price, the corner they have mentioned the price also, it will be above 1 lakh or 2 lakhs, 3 lakhs, that range. But you can see that quantum dots are, can give you very vivid colors, right? Lively colors, right? The real colors. But the price is huge nowadays. Probably at some point of time, it may come down, right? So as you know, quantum dots are nothing but semiconducting nanoparticles, very small size. So you can just, I am just showing you some quantum dots with different colors. So you can see a blue light is as a excitation at 450 nanometers. And you can see that the quantum size, quantum dot size is 2.5, 3, 5, and 6 nanometers, right? And emitted light will vary. The wavelength of emitted light will vary depending on the size. So usually you can see that smaller the size, larger the band gap of these quantum dots, and that will be excited by higher wavelength. So you'll get a blue light when quantum dot size is small, right? So the same aspect actually we are also using in display devices, right? So we can use quantum dots to improve the performance of LCD systems, right? So you can see that um, we have a variety of materials are nowadays available, right? And so basically the principle is like this: the semiconducting quantum dots, the process corresponds to the transition of an electron from the valence band to the conduction band. The excited electron can drop back to the valence band and releasing its energy by the emission of light. So the color of that light depends on the energy difference between the conduction band and the valence band. Right? So basically we are looking at the band gap, right? So as I told you, in the quantum dots, as the size goes down, the band gap increases. So similarly, when you use it for display applications, you can tune the colors, because basically in most of the cases we are actually not changing the LCD as such. On the color filter, as I told you, we have a red, green, and blue. In the color filter, people are starting using quantum dots, right? So so you can see that these are wonderful colors you can expect from quantum dots. So you can see this is larger quantum dots, that is size is around 5 to 6 nanometers, emit longer wavelengths, orange or red, and smaller quantum dots 2 to 3. So you can see that they emit shorter wavelengths, blue or green. So you can see different colors. But remember, the excitation is only for 450 nanometers, the blue light, right? But it's giving you different colors like this. So you can see this variety of wonderful colors. So this is actually from the photoluminescence associated with the cadmium sulfide or selenide or zinc sulfide materials. So by mixing different, quantum dots, you can tune the colors, right? That means for a particular application. In our case, we need only red, green, and blue. In such cases, you can tune the color by mixing different type of quantum dots, right? So so this is the fluorescence spectra of each quantum dots of varying size. So you can see the 2 nanometer, 2.5, 3, 5, and 6 different colors are coming out from the quantum dots, right? So if you can play with the synthesis part of the quantum dots, so you can tune the colors, right? So if you look at the color spectrum of conventional television, that is a conventional LCD with quantum dot TV, you can see that the colors will be like this. You see that the conventional TV, the color will be something like this. Whereas for a quantum dot television, you can see that the color spectrum will be like this, which means that the purity or the quality of color, right? If you say red, the quality of red, or if it's a green or a blue, the purity of the color will be very high when you start using these quantum dots, right? So that way, your display performance will be improved, right? So for example, in this case, they are using cadmium selenide or cadmium sulfide, right? Even the cadmium is a little bit heavy metal poison chances are there, but still people are using. And as alternate, people are working on zinc-based materials or other materials which are less toxic, right? So we can, in this case, we can see that this is the blue LED. We have a phosphor material, and this is the pixel. This is from the red, green, blue. Whereas in this case, you can see that the phosphor is replaced with quantum dots, right? The phosphor is replaced with quantum dots, and you can see that the color is obtained is almost 64 times better than a normal LCD screen, right? So you can see 1 billion colors. This is 16 million colors. So that much colors is possible when we start using the quantum dots, right? And in the quantum dot displays, you can use different aspects. One aspect is you can see that start using a quantum dot film. So they are actually inserting a extra film here. You can see this is a quantum dot film. So you have a backlight, which is a blue LED, but in this case, you are using a white LED because to get these colors, we need a excitation wavelength of 450 nanometers, right? So that's why we are going for this blue LED in this case. But in normal LED, we are using white LED is sufficient, right? Because here we are only using color filters, normal color filters, standard LCD. But in this other side, you can see that you are introducing an extra film, which is a quantum dot film, right? So the quantum dot will give you improve your colors, right? Because you are getting a better colors from the quantum dot emissions, right? So that way, your improvement on your display performance you can expect, right? And other option is to convert your conventional color filters with the quantum dots. You can see that we have blue LED here, and you can see the color filters are replaced with blue quantum dots, green quantum dots, red quantum dots, like that. So that way also you can do, right? So this is a little bit different configurations. Previous case we have just introduced one film in the backside, but in this case the color filters as such are replaced with quantum dots, color filters, right? So these are you can see that some quantum dot based methods. One is quantum dot sheets. So just introducing one quantum dot sheets here, and we are getting the different colors. So I think this is already in the market, and we have something like a quantum dot glass. So that means on the quantum dots can be introduced on the glass plate, then can be introduced here. That is in the front panel, and we have a quantum dot pixels. Right, so pixels itself will be a quantum dot, right? So, but we have a blue LED in the back side. So each pixel is a quantum dot. Then they will produce its own color, right? Then latest development we can consider it as quantum dot electroluminescent, right? Electroluminescent. Actually, this is completely different. So you can see that in this quantum dot electroluminescent, we are actually generating its own colors, right? You don't need any backlight. Backlight is not required. Quantum dot itself can produce light, red, green, and blue. Then each pixel it can have its own light, isn't it? But in other cases, a blue LED backlight is required, right? But in this case, the electroluminescent based system, it will be something like this. You see that you have a glass substrate, we have a whole transport layer, we have a quantum dot emissive layer, then we have a electron transport layer, something like a solar organic solar cell or a light emitting diode, organic light emitting diode configuration. So active materials is a quantum dot material, and this is how it happens. So you have a red, green, and blue, different colors. Then light can be produced, right? So this will be maybe the future technology. So the idea is that this can give you original colors. So your light which is produced from each pixel. You don't have a backlight. You don't need a LC electrical material, right? You can control individual pixels, right? So the color quality will be huge, right? So no comparison with any other display systems, right? Maybe of course the cost will be huge. Definitely, maybe at some point of time there will be a change in the cost as well, right? But so this may be some promising display systems. And other than that, you can think about organic LEDs also, where it is similar to this one. Organic LEDs, each pixel will give its own light. You don't need any backlight or LCD. So thickness of the display system can be reduced considerably, right? So much of work is going on in this area. And we can have perovskite based corner dots. So this is perovskite material. You can say cesium, lead, chlorine, bromide material. This is perovskite material, and you can see different colors coming out. This is the blue material, this is the green material, and this is the red material. So you're just playing with composition of this material. They are making such display devices, right? So this is also another hot topic because most of the organic materials has chances of degradation. But this type of perovskite based material, which are inorganic in nature, and that will not undergo any sort of degradation, so they have a long life. So compared to the conventional organic molecules, right? So maybe we will see this type of display also in future, right? So you can see beautiful colors from this corner dots, and to conclude, you can see the different type of display systems, how it is coming up. We can see that we have LCDs, we have OLEDs, we have corner dots, we have micro LEDs, etc. are coming up. So micro LEDs based displays are also coming up, where the pixel size is too small. They are making very small LEDs. Then each LED will give you its own color. So you don't need any backlight or anything like that. And as I told you, when you go for LCD, why we are going behind LCD is that for the time being, it is the cheapest one available, low cost, and it is highly saturated. I mean, mature technology, and still the largest market share. Maybe at some point of time, like the CRT replaced with LCD, maybe at some point of time, the LCD will be replaced with the micro LEDs or I don't know, corner dot or something like that. So there is every possibility, especially huge companies like Samsung, LG, Philips, etc., are behind to introduce such type of devices, right? And maybe flexible devices, foldable devices, rollable devices. Those are also you can expect, right, in the coming future. So there's a huge market for the display because this is literally an entertainment market, right? So everybody love to watch wonderful videos on this type of flat screens. So there's huge huge business. So to sum up, so probably I have tried to explain the optics, the electronics, the materials which are involved on this LCDs devices, right? So with this, I conclude today's session. If you have any questions, we can discuss. Thank you.
Thank you, sir. Participants, if you have any questions, you can ask him. Please feel free to ask any questions.
Or if you have any questions, you can type on the chat box as well.
Yeah, you can type your questions in your chat box so that he'll be answering to your session. Okay, sir. Then, on behalf of MESCE College of Engineering and participants, I would like to thank I would like to show our sincere gratitude to you, sir. We had an elaborate session on LCD displays. Okay, sir. Thank you, sir.
No, thank you. Thank you so much.
Next session starts at 3:30 p.m. So we have a 15-minute break. Okay. Please join at the earliest. Thank you.
ഹലോ ഷൈൻ ഉണ്ടോ?
യെസ് മാഡം, യെസ് മാഡം.
ഉണ്ടല്ലേ. ഞാന് ഇപ്പൊ എല്ലാം ഒന്ന് അഡ്ജസ്റ്റ് ചെയ്ത് വന്നതാണ്. മുജീബ് കേറിയോ?
ഇല്ല സാർ.
ആയിക്കോട്ടെ ആയിക്കോട്ടെ ആയിക്കോട്ടെ. എനിക്ക് എന്തെങ്കിലുമൊക്കെ പറയാൻ വെച്ചേക്കുന്നേ എന്താ. ഓ,
ഞാൻ തുടക്കത്തിൽ തന്നെ വിളിക്കും.
എന്നിട്ട് ഞാൻ നിന്നെ ബ്രീഫ് ചെയ്യാൻ പറയും കേട്ടോ.
വേണ്ട, ഞാൻ ബ്രീഫ് ചെയ്തിട്ട് മിസ്സിനെ വിളിക്കാം.
ആ ശരി ശരി ശരി. ഇത് ഓഡിബിൾ അല്ലേ? ഞാൻ പറയുന്നത് ഓഡിബിൾ അല്ലേ?
Yes.
ആ.
Hello, Mujeeb sir. Sir, good afternoon. I think sir has joined. Mujeeb sir.
മുജീബ്. ഹലോ മുജീബ് സർ.
ഗുഡ് ഈവനിങ് മാഡം. ഗുഡ് ഈവനിങ്.
ഗുഡ് ഈവനിങ്. ഹായ്. ഒരു വ്യത്യാസം ഇല്ലല്ലോ.
ഓക്കെ, സുഖമായിരിക്കുന്നല്ലോ അല്ലേ?
ആ, സുഖമായിരിക്കുന്നു.
ഓക്കെ.
പിന്നെ എങ്ങനെയുണ്ട് ജീവിതമൊക്കെ? സുഖല്ലേ?
അതെ അതെ, വളരെ സുഖമായിട്ട് പോകുന്നു. ഇപ്പം ഞാൻ ഇന്ന് വീട്ടിലാണ്.
വീട്ടിലാണല്ലേ? വൈഫ് ഇപ്പൊ എവിടെയാ?
ട്രിവാൻഡ്രം മെഡിക്കൽ കോളേജ് തന്നെ. ട്രിവാൻഡ്രം മെഡിക്കൽ കോളേജ്
അവിടെ തന്നെ. മക്കളൊക്കെയോ? മക്കളൊക്കെ എന്തായി?
മൂത്താള് ബിടെക് കഴിഞ്ഞ് അങ്ങനെ ജസ്റ്റ് നിൽക്കുന്നു.
ആ, ഏതായിരുന്നു?
ഇലക്ട്രോണിക്സ് ആൻഡ് കമ്മ്യൂണിക്കേഷൻ.
അത് ശരി. ആ,
രണ്ടാമത്തെ ആള് 10th കഴിഞ്ഞ് +1 ജോയിൻ ചെയ്തു.
ആ, അത് ശരി. ആ, എന്താ ബയോമാത്സാ?
അതെ അതെ അതെ, ബയോളജി സ്ട്രീം.
ആ, അത് ശരി.
ഓക്കെ.
പിന്നെ അവിടെ ക്വിസാറ്റിലൊക്കെ നന്നായിട്ട് പോകുന്നില്ലേ?
നന്നായിട്ട് പോകുന്നു.
അപ്പൊ ഇത് നമ്മുടെ ഒരു പഴയ ഓർമ്മ പുതുക്കലാണല്ലേ? MESന്റെ ഒരു ഫാക്കൽറ്റി ആയിട്ടല്ലേ? അല്ല, ഇവിടുത്തെ FDPക്ക് ഒരു ഫാക്കൽറ്റി ആയിട്ടല്ലേ?
അതെ അതെ, വളരെ സന്തോഷം.
ആഹാ.
ഓക്കെ.
മുജീബ് എന്നും പോയി വരുവാ?
അല്ലല്ല, വീക്കെൻഡില് ഫ്രൈഡേ ഈവനിങ് വരും, മൺഡേ മോർണിംഗ് പോകും.
ഓ, അത് ശരി. ആ, അവിടെ ഹോസ്റ്റൽ ഉണ്ടല്ലേ?
അതെ അതെ, ക്വാർട്ടേഴ്സിലാണ്.
ക്വാർട്ടേഴ്സ്.
അതെ അതെ അതെ. ഇതിപ്പം
മുജീബ് ഉള്ളപ്പോ സുനീഷ് ഉണ്ടായിരുന്നോ?
ഇല്ല. ഞാൻ ഫിസിക്സ് അല്ല, അപ്പൊ ഞാൻ പോയാലല്ലേ സുനീഷ് വരുവുള്ളൂ.
സാറ് പോയിട്ടാണ് ഞാൻ വന്നത് മാഡം.
ആണല്ലേ? അല്ല, അന്ന് മുജീബ് മാത്രമേ ഫാക്കൽറ്റി ഉണ്ടായിരുന്നുള്ളൂ. പിന്നാണ് സ്ട്രെങ്ത് കൂടിയപ്പോ നമ്മള്.
ഇപ്പൊ ഒന്നിലധികം പേരുണ്ടല്ലേ?
ആ, 3 പേരുണ്ടായിരുന്നു. ഇപ്പൊ ഒരാള് വീണ്ടും പോയി.
ഓക്കെ. Dr. Sunish, shall I share my screen?
Yes, sir. Actually, we have given a 10 minutes break between session 1 and...
No problem. Let us wait. No problem.
Okay, sir.
So, because it's a very pleasure for me to interact with other professors like Professor Ahmed Madam, because we were together for many years.
It is not just like a colleague, more than that.
And we are also privileged to have you, sir, as a resource
Yes,
person
yes.
for this faculty development program.
Thank you very much. I think my slide is visible, right?
No, sir, it is not. Right now, it's okay. Right?
Yeah, it is coming. sir.
Yes.
Yeah.
Yes.
So, Sunil sir, shall we start?
Yes, sir. Please.
So, third day's last session, we have eminent personnel, Dr. Mujeeb. He's an accomplished academician with more than 26 years of teaching experience, both in engineering colleges and in university departments. He's currently senior professor at International School of Photonics. He was director of school from 2016 to 2019 and on deputation to the government of Kerala as joint director and director of LBS Center for Science and Technology during 2012 to 2016. He did his PhD in optoelectronics at Rocket Propellant Plant, VSSC ISRO Trivandrum. Apart from regular teaching and research with more than 65 publications in international journals, 80 conferences, he has proven track record as a good administrator with ability to lead organizations under higher education and served in chief executive board of 3 different universities in the state, USAT, KTU, and MG University. I would like to invite Dr. Rahmatunsa, HOD Mechanical, to welcome him. Please, madam.
Thank you, Shaheen. A very warm good evening to one and all. We are proceeding to the third day of our ATAL Faculty Development Program on Photonics and Laser. On behalf of the MES College Management, FDP coordinators and participants, I take the privilege to welcome Dr. Mujeeb. Presently, he serves International School of Photonics, QSAT, as a senior professor. As a colleague and friend, we know each other for more than 26 years, and he is more than a colleague to me. He was the director of school from 2016 to 19 and served Government of Kerala as Joint Director of LBS Center of Science and Technology. I feel proud to say that he is the apt person to chair today's session. He has more than 65 papers in his credit and well known as a capable administrator. He is a member of syndicate for 3 different universities, QSAT, KTU, Kerala Technological University, and MG University. I feel so much pleasure and pride to welcome Dr. A. Mujeeb to share his insight and perspectives with the gathering for the benefit of all. Hearty welcome, sir. Thank you.
Thank you, madam. Am I audible?
Yes, audible.
Yes, please. Good evening. Thank you, Dr. Shaheen, for the nice words. Dr. Sunish, coordinator FTP, for inviting me. I'm very happy to be here. This as part of AICT ATAL FDP organized by MES College of Engineering. In fact, my happiness is because that this is organized by MES College of Engineering, where I spent nearly 8 years of my service, my initial service as a lecturer in physics, that from the very inception of this institute in 1994. I had received immense experience both in curriculum, co-curricular and extracurricular activities, and that has molded me as a good administrator or teacher. Whatever you have given me as a recognition is only because of my service that I have rendered in MES College of Engineering. In fact, it is a great pleasure for me that Professor Rahmatunsa Madam, Professor of Mechanical Engineering, was my own elder sister during that period till now. Even now, I am keeping and cherishing my memories and affection with her. And I'm happy that she is also one of the organizers and also a participant here. With these words, let me start my presentation. It is optical non-destructive testing. Actually, this is a very interdisciplinary participants group, as informed by Dr. Sunish. My today's talk is intended mainly for mechanical engineers, physics, and computer science groups. So we will be continuing our discussion tomorrow also. So before discussing the optical non-destructive testing, let me give a very brief introduction about our campuses in Cochin University. We have three campuses. One is the main campus, other one is the Lakeside campus, and the third one is Alappuzha. These three campuses are the academic building blocks of Cochin University of Science and Technology. We have specialized centers like Advanced Center for Atmospheric Radar Research, ACAR, which will be giving daily weather forecasting to community, agriculture community, and many others. Second one is a Science for Center for Science and Society, that is CIS, which inculcate scientific temper to school children. And the third one is a Sophisticated Testing and Instrumentation Center, which all the research groups all over the country, all India level, may be knowing this facility, because every researcher need this instrumentation center. Then we have a Center for Innovation, Technology Transfer and Industrial Consultancy at QSAT. Located in Cochin, at Cochin University of Science and Technology, we have specialized specific courses which is specifically meant for region, like ship technology, polymer technology, marine geology, geophysics, biology, industrial fisheries, seafood processing, meteorology, marine engineering, etc. This is the only university which is offering such a different region-specific courses. Of course, we have specialized courses like Photonics, Safety and Fire Engineering, Intellectual Property Rights, Marine Biotechnology, Biopolymer Science. I am belonging to this department, that is Photonics department, which is named as International School of Photonics. Of course, we have received many awards and recognitions in QSAT, also for ISP. As per the NAC report, from among the 31 departments in the Cochin University, 3 departments were identified as excellent departments, and I'm happy to state that ISP is one of the 3 departments. We have received a Chancellor's Award instituted by the former Chancellor, Sadashivam. After that, we have received 3 times we have received a Chancellor's Award, 2017, 19, and 20. This is Ms. Divya Bharati, was a student of International School of Photonics, who stood all India first rank in GATE physics recently. She got 100% for GATE rank. Cochin University is ranked as 24 in National Institute of Ranking Framework in 2021. We have a number of collaborative projects and internship with different national institutes all over India, RRCAT, IASC, IIT, ISER, Kolkata, Saha Institute, Kolkata, etc. And a number of students are having sandwich programs from International School of School of Photonics to other international institutions like Multimedia University, KAUST, Saudi Arabia, Nanyang Tech University. Many universities are on the list. Of course, we have in photonics research field, many faculty members and researchers pursuing photonics or physics research. For their understanding, let me give you a brief instrumental facility of our department. We have sub-picosecond laser, which is one of the lasers available in South India. Then spectrophotometer, Nd:YAG lasers, different Nd:YAG lasers are available. CCD spectroscope, Z-scan for nonlinear measurements, optical fiber drawing facilities there. Then film thickness measurement, number of facilities are there. We used to share these facilities to other research communities, where some limited facilities are available for others too, with some payments. My research interest, which is given on a single slide, actually I'm working on 3 different areas of research. There is laser spectral metrology and nanophotonics. And recently I have started.
Excuse me, sir. Sir, excuse me. Can you make it in presentation mode?
Yeah, this is a presentation mode. Okay. Yeah, this is a very, very small letter side because I have incorporated everything in a single slide. Okay, next slide onwards, I think more visible.
Okay, sir. No, I'm asking you about pressing F5 because the screen is so that we can move on to the full screen mode.
Yeah, actually it is full screen, but my laptop is small in size. That may be the reason. It is 4-inch laptop.
Okay, sir. Okay. Fine.
Okay. Yes. So here recently I've started the wireless ad hoc networks research with some faculty members working in government and aided engineering colleges. Main work is about nanophotonics and laser spectral metrology. In laser spectral metrology, one of the items that we are doing is non-destructive testing. So this area, this non-destructive testing area I'm discussing today, and laser spectral metrology in detail we'll be discussing tomorrow. This is the outline of my talk today. I think this is visible, right? More or less is quite visible. Yes or no?
Sir, it's visible, but the screen is not. You have to.
I think screen is not moving. Mujeeb sir, slides മാറ്റുന്നുണ്ടോ sir?
Yeah, I am changing the slide.
But slide change ചെയ്യുന്നില്ല. അതെ ഷെയർ സ്ക്രീൻ അത് കൊടുക്കേണ്ടി വരും. അല്ലെങ്കിൽ ഇവർക്ക് അങ്ങ് അയച്ചു കൊടുത്താലും മതി.
Let me. Okay.
Sir, F5 press ചെയ്താലും മതി. F5 press ചെയ്താൽ presentation മോഡിലേക്ക് പോയിക്കോളും. Full screen മോഡിലേക്ക് പോയി.
Okay. Wait.
സാർ ആദ്യം മുതൽ കാണിച്ച സ്ലൈഡ് ഒറ്റ സ്ലൈഡിൽ നിൽക്കുക.
Oh, yes. Sorry. Okay.
അതാണ് കമന്റ്സ് വരുന്നുണ്ടായിരുന്നു.
Sure. Okay. Please wait. Okay. Actually, I have presented different slides. Okay.
But അത് വിസിബിൾ അല്ല.
Okay. Is it visible now?
ഇപ്പോഴും ഫസ്റ്റ് സ്ലൈഡ് ആണ് സാർ, ഒന്ന് മൂവ് ചെയ്ത് നോക്കേ.
Okay. Is it visible first slide? The second one is visible?
No.
Is it not visible?
Not visible, sir. Not visible. അതായത് സാറ് സ്ലൈഡ് ഇപ്പൊ വന്നു അല്ലേ?
Now is it visible?
സാർ ഒരു സ്ലൈഡ് കൂടെ ചേഞ്ച് ചെയ്ത് കൊടുത്തു നോക്കേ.
Now is it visible?
Yes, sir. Now it is okay.
Okay. So the slides are changing.
Okay.
So I have been discussing about the facilities of Cochin University, like specialized centers, ACAR, CSIC and CITIC. Then region-specific courses like different courses like ship technology. All these things I have given. I hope slide is changing now, right? And specialized courses like photonics, safety, fire engineering, intellectual property rights. Is it visible?
Yes, sir, visible.
Yeah. So this is a slide that I have shown that is regarding the awards and recognitions of QSAT, ISP, that is different Chancellor's Award we have received. And this is the photograph of Divya Bharati, our student, who received a GATE first rank, all India first rank, got 100% for her GATE score. So I have discussed about the collaborative projects, that internships and projects with different national institutes all over India. Then I've shown you the internships and fellowships and projects with the different universities abroad. That is Multimedia University, Malaysia, Tampere University, KAUST, University of Illinois, USA, etc. This year also 6 students of our MTech batch went to different universities abroad for completing their second year MTech projects. We have some teen program. Some members from foreign universities are coming here. Some students we are sending from ISP to other recognized research centers abroad. Dr. Sunish, can you see this slide, Photonics research facilities? Let me make sure that it is visible.
Yeah, yes, sir. But it's not in the full screen mode.
Yeah. Let me.
You can make it by pressing F5.
Yeah. This is fine.
This is fine. We can see the slides, but it will be more attractive if it is in the full screen mode presentation.
Actually, this is in the full screen mode. Let me change the next slide. Is it changing now?
No, now it's on the 9th slide. See?
Yeah, it is not changing.
Not changing.
Okay.
Ninth one. Photonics. Yeah, now it's okay. It's on the 10th one.
Okay, so let me make. Okay. Yeah. This is my research field that I have given you. Today I'll be discussing about one of the topics of laser spectral metrology, and some other works of my interest are wireless networks, nano biophotonics. So this is the outline of my topic. Though the topic is optical non-destructive testing, I'll be giving a brief introduction on optics, its origin and nature, for better understanding of other disciplines for other teachers and faculty members. Then I'll be coming to optical non-destructive testing, then holographic non-destructive testing, then speckle non-destructive testing. The two optical non-destructive testing methods that we are going to discuss are holography and speckle. I'll be giving a brief introduction on holography and speckle, then we'll be coming to the research prospects. So let me ask a question, because this is an FDP for lasers and photonics. So everything that we are discussing, you are hearing yesterday onwards till the 5th day or Friday is regarding light. When did you start wondering on light? Because even we could not answer this question, because even we may not remember when we have started such an experience of wondering on light. So we have been discussing such a technology that is an electromagnetic spectrum. That is, we discuss, International School of Photonics mainly discuss this visible area of electromagnetic spectrum. That is the wavelength ranging from 400 nanometer to 700 nanometer, or 380 nanometer to 680 nanometer range. In some experiments, we also do some experiments on ultraviolet region and infrared, but mainly focusing on visible region using lasers. So laser is the powerful tool that we have been using for all the experiments. Let us discuss something on origin of light also. What is origin of light? You may be knowing all these things from your +2 course onwards, or BSc physics or degree level physics. But let me ask a question. Who is considered to be the scientist who did experiment to know the secret of light? Many are having a misbelief that it was Sir Isaac Newton. But remember, about 600 years before Newton, there was an Arab scientist who studied the nature of light through experiments. His name is Abu al-Hasan ibn al-Hasan ibn al-Hayatam. we used to call him in photonics community known as Ibn al-Haytham. So Ibn al-Haytham is considered as the father of photonics or father of light, who has given the insight or secret of light. In his book, this is the book written by Ibn al-Haytham. The book name is Kitab al-Manazir, in which Al-Hasan correctly identified that eyesight is caused by light entering the eye, contradicting an earlier belief. It was believed that light is emitted from the eye. So that contradiction was corrected by Al-Hasan. After that, we have been studying what is light. Light is a particle, whether light is a wave, and we know light is both as a particle and as a wave. So, let God said, this is a word, this is a lines from Genesis, from Bible. God said, let there be light, and there was light. Einstein said, let it be quantized, and there was photonics. When we study the technology of light, we call it as photonics. When we study the science of light, we call it as optics. That's the main difference. So here we used to deal both optics and photonics, both the science and technology of light. I'm giving some of the characteristics of photons and photon energy. Gamma rays are most powerful, 10 to the power of 5 electron volt. But visible light is having only 2 electron volt. In visible light, red to violet to red, BIB0 is the region. R lambda, red is having higher wavelength. Violet is having lesser wavelength. So E is equal to h nu. So when we consider a photon of visible energy 2 electron volt, so when you consider a cup of water, if every molecule suddenly absorbed a red photon, the temperature will shoot up to 10,000 degrees centigrade. So you can consider there is a cup of water can be raised to a temperature of 10,000 degrees centigrade with a photon of 1.6 electron volt. That's many red photons can be absorbed in a cup of water. This is the powerful nature of photon energy. That is what we call it as laser. These are the 4 fundamental or the basic equations that we require for photons. One of the nature's most popular methods for packing energy with very little mass and momentum. It is just like for a sports car. So energy E is equal to h nu is the first equation. Lambda wavelength is c by v nu. Then momentum P is equal to h nu by c or E by c. Then mass is equal to E by c square. These 4 equations will give you better understanding of photons. So some more diversions or extra equations are required for better understanding, but these are the 4 main essential equations. So here let me say, according to Max Planck, the photons which constitute a ray of light behave like intelligent human beings. Out of all possible curves, they always select the one which will take them most quickly quickly to their goal. That means photon is considered as a human being. So it can do its own way to reach its path. That we used to study this as like Fermat's principle of least time, or in mechanics we used to say Fermat's principle of least action. Many theories and many equations and laws are there. Now, with this introduction about light, let me discuss non-destructive testing. Non-destructive testing, these slides are visible, right? Yeah, though it seems small, it's are visible, right? Hello?
Yes, sir.
Yes. Okay.
Yes, sir.
Yes. So this is a non-destructive testing. Nothing new in the science and technology of non-destructive testing. When a coconut is plucked from a tree, this worker will have some methods to check whether the coconut is ripened. He is simply shaking the coconut or doing something else, and he says this is a ripened one. That technology is what is called a non-destructive testing. It is not destructed. When he pluck and cut the coconut, and whether he is verifying it is a destructive evaluation method. So even now, when we purchase a pot, or grandmother or mother is purchasing a pot, there are some methods. Then they will look into the pot, inside of which where there is a small hole by which light enters. That is a method for non-destructive evaluation. These are simple techniques, not based on science and technology, but by common sense, that we have non-destructive testing methods. So what is the purpose of science and technology of non-destructive testing? We may require highly sophisticated instruments. For example, in a GSLV, PSLV component in ISRO, or in other applications, we may require a complex structure that may consist many materials and structures. So while fabricating these materials, there may be defects that can occur during the complex manufacturing process. So we require non-destructive testing, which is essential for assessing the quality and reliability. There may be cracks, voids, inhomogeneities, many other faults are there in the manufacturing process. These are some of the sophisticated instruments. There is thousands and thousands of crores of rupees are spending for such vehicles, so space vehicles technology, where we need very good non-destructive testing methods. So what are the conventional non-destructive testing methods? Radiography is one of the methods. X-ray is used. For medical technology also it is used. Ultrasonic testing method is used. Dye penetrant testing is used. Magnetic penetrant testing is used. Eddy current testing is used. But there are certain limitations depending on the materials to be tested. For example, if I want to test a low modulus materials, when the Young's modulus is very small, we cannot use this radiography ultrasonic. Why this Young's modulus low material is very important? Because we know in VSSC space vehicle components, we use these low modulus materials as insulators. In this case, what happens? Radiography often fails in detecting planar defects and fine cracks. So we cannot use the radiography. In the case of ultrasonic testing, there are some limitations. It attenuates acoustic. We cannot use some materials which attenuates the acoustic energy. Then microwave testing is also not feasible in some cases because some useful techniques then that limited sensitivity for defect detection. Dye penetrant, magnetic penetrant, and eddy current also not feasible in some cases. So in that case, what we are using is optical techniques. That is optical techniques and advanced NDT techniques. There is computer tomography, acoustic emission, microwave testing. These are advanced techniques. In optical techniques, what we use are holographic non-destructive testing and laser speckle non-destructive testing. My today's talk is limited to these two techniques. There is holographic non-destructive testing and speckle non-destructive testing, with a brief introduction on these two things for the beginners or the other disciplined faculty members. Why these optical techniques are important? The optical techniques are important because, the optical techniques are non-intrusive, they are non-contacting, they are highly sensitive, they are full field measurement, real time and accurate. Then here, it is very important that, let me say, it is highly sensitive. How much sensitive an optical experiment? You can imagine the wavelength of light. Wavelength of light, I told you that it is 380 nanometer to 780 nanometer. So even half the wavelength, or lambda by 2, that is, if you consider a 600 wavelength lambda or of light, 300 nanometer is the sensitivity. So sensitive the optical methods are. That is why we are very much interested on these optical methods. Now, let us discuss holography. Holography was first invented by Dennis Gaber. Actually, hologram is a 3D image recorded on a photographic plate using a laser. Holography is a very interesting optical phenomena or light phenomena, which was fascinated by other researchers too. For computer science students, they are working on holography as a memory storage device. For mechanical engineers, you can use it as a holography as an entity tool. For forensic medicine students, they use this holography as a tool for security, for forensics. Many number of applications are there for this holography. Let me give you a brief introduction on this topic also. After that, I'll come to the non-destructive testing and the research aspects. The recorded image, the holographic image of the object, contains whole optical information. That is, it is having amplitude and phase information. Then when you consider an imaging, for example, when you consider imaging and a holography, or a photography and a holography, in imaging, there is a recreation of the object information, usually using the amplitude information. The phase is not used there. There is no depth information in a photography. Only we are projecting the 2D projection of a 3D screen. But in holography, we use this interference phenomena. Interference, you might have studied light interference in your +2 course. One wave is falling over the other, and we get some dark and bright fringe pattern. So using that interference phenomena, we capture the phase information, because phase is very important in holography. What we are getting is the depth information, and this holography is a two-step process. Its history can also be given. I told you holography interference is a very important information, or the technique, the property, for interference we require complete coherent light. For which is the best coherent light? Laser is the best coherent light. So even though Dennis Gaber discovered this holography in 1947, optical holography advanced only in 1960. The reason is, laser was invented during that time. Practical laser was used for recording hologram by Leith and Photonics in 1962. With the invention of laser, not holography alone, all the properties and techniques and information is involved in photonics or optics were tremendously improved using the lasers available at that time. Even now we have been using the same technique, that is the laser as a source. This is the timeline of holography. 1947, Dennis Gaber discovered it. 1971, Dennis Gaber received his Nobel Prize for this discovery after the verification of this white light holograms using lasers. That is by Leith and Photonics. So, what are the experimental setup we require for holography arrangement? We require a laser. That is a laser. Even small lasers will be giving you best results. Diode lasers or laser helium neon laser. Small power lasers are also good for doing experiments like 2 milliwatt or 5 milliwatt. If it is a 15 or 25 milliwatt, it is well and good. We need a beam splitter to split the light. We need a hologram plate, just like the photographic plate is a silver halide emulsion is required for recording the holograms. So as I told you, the hologram is involving two holograms processes. There is the first one is called recording. In the recording process, we irradiate the object. The object is irradiated with a laser beam. A single laser is used. A beam splitter is used to split the beam. Okay, it is splitting into two. One beam is made to fall on the object and the other beam is directly made to fall on a mirror. This is considered as a reference beam. This is the object beam. Both the object beam and the reference beam are made to interfere on another holographic plate. This holographic plate, that is hollow plate, will give you a hologram. That is a fringe pattern. This is the first part, we call it as a recording. Then the second part, that is we use to reconstruct the image from the virtual image, that is from the object. We use to irradiate light. Here, laser is not necessary. Even we can use white light or some other source for reconstruction. That means the first part, recording of hologram, interference is involved, and coherence is involved, laser is essential. In the reconstruction part, we can use any light, not necessary for coherent light. So, what we are getting is we can reconstruct object with a tiny piece of hologram. A hologram may contain a number of consecutive recorded scenes that can be recorded independently. So there are many theories. I'm not discussing the theory in detail. Remember, the light can be represented as equations. You may be knowing light equations for interference equations, but for hologram, we can represent the object wave as an equation, reference wave as an equation. At the recording plate and transmitting plane, we have equations. I'm not discussing that equations in detail. So you can refer some textbooks on holography, will be giving you all the theory behind holography. In reconstruction process also we have equations, that is T of xy, R of xy, which governs in terms of intensity and amplitude. So understanding the generated beams after holograms, we require a thorough understanding of all these equations. Which equation or which wave is governing the reference wave, which one is the object wave, which one will be giving the conjugate of the object wave, etc. Based on this theory, we can even generate computer holograms that are giving later session when we discuss the types of holograms. So using these equations, using MATLAB programming or even C++ programming, we can generate computer holograms also. These types of hologram, there are different types of holograms like a transmission hologram, reflection hologram, etc. 360-degree holograms and digital holograms. This is what I told you. Holography is based on recording both the amplitude and phase. Digital holography is an advanced technique in which hologram is recorded digitally and reconstructed numerically in a computer. Hologram coded as a bright and dark micro fringes. These are called micro fringes. These are the micro fringes from which we can see we can reconstruct the image. When you see a hologram, directly you cannot see the object. It is visible as a fringe pattern. But when we reconstruct only, the fringe pattern will be giving you the object. This is a digital holography setup. This is a CCD camera. So the CCD camera light is split into two. This is a beam splitter. This is a cube beam splitter. There are beam splitters, that is a plate beam splitter and cube beam splitters, in the split into two, and the two beams are made to interfere and is made to fall on a CCD camera. The computer generated holograms can be produced using the CCD cameras. So there are a number of applications, as I told you, for holograms: 3D imaging, data storage, interferometry, dynamic holograms, security holograms, etc. But my interest is in research is HNDT, that is holographic non-destructive testing. So far, I have given you a brief introduction on holography. So how can we use this holography for non-destructive testing? That is, we have some techniques in holography called double exposure, real-time holography, time average holography, sandwich holography, heterodyne holography. Out of these techniques, I'll be giving only one technique here for the time constraints, that is a double exposure. In these high holographic interferometer techniques for non-destructive testing, we use a number of loading methods. That is, number of loading methods means we may use either mechanical loading or thermal loading or vibration loading or pressure loading. So I will give you the information in the next 2-3 slides, how we perform HNDT. See, this is a holography setup as I told you earlier regarding recording and reconstruction. In the recording process, what you are getting is a fringe pattern. Not the object directly, but a fringe pattern. Only on reconstruction stage only you will be getting the actual object of this material. So in this case, what is the technique used in non-destructive testing? In the non-destructive testing, double exposure, initially we take the hologram of the object, first hologram. In the second case, what we do is, we simply stress the object. We load the object after giving a minute loading. Either mechanical loading I told you, or temperature loading or vibration loading. When we stress the object, what happens? There is a path difference or a phase difference occurs. Remember, this small change, this minute loading will not affect the object. Don't misunderstand that this will destruct the object. No, this loading is very, very minute, because it has to shift the fringe, that's all. It has to shift the fringe by lambda by 2, or a small interference changes, or we can say it is a small phase shift. So this is the technique of holographic non-destructive testing. With this best understanding, what I'm doing is I'm just sharing you some of my research works on laser holographic interferometry that we have published in the British Institute of Non-Destructive Testing, and also how to design a non-destructive testing facility, how thermal deformation analysis of aluminum heat using electronic patterns, speckle pattern, etc. can be used for research. So my talk is based on these 5 research papers that we have published, and it's a Russian Journal of Non-Destructive Testing, how to detect and analyze micro cracks in low modulus materials, and how to detect the various surface roughness parameters of low modulus aerospace materials. My slides are changing, am I sure? Let me make sure that whether the slides are changing.
Yes, sir, your slides are changing.
Yeah, all the 5 papers I have shown you. So there's some researchers. So this is one of the experimental setup that we use in our laboratory. So this is a diode laser, 532 nanometer laser. This is a spatial filter. That spatial filter will reduce the noise of the laser beam. then we are having a mirror here. This is the object. This is a CMOS camera, or you can use a CCD camera, and it is connected with the computer. So this is animation. Can you see the animation here? That is laser is passing. Yes or no?
Yes, sir. The animation is visible.
Yeah, the laser is passing. So that is, we can see that after this, what we are getting is the object fringe pattern. There is a fringe pattern on the laptop. This fringe pattern will give you the recording of the hologram. So remember, this recording of a hologram is not simple as that I have shown you. The minute loading is very sensitive, for which we require a vibration isolation table. The vibration isolation table is very important. Even it should not capture the vibrations in and around. So now I want to detect the voids, that is the defects in this cylinder. I have to take the holograms of this metal tube. There is a whole metallic tube is used as a test specimen, which is thermally loaded using a heat power device. And a reference hologram is recorded initially, and successive holograms are continuously recorded. Then what we are doing is that holographic fringe patterns are then processed. You know, this is a fringe pattern. Some of you may be knowing about the Newton's rings experiment, air wedge experiments, the simplest interferometric experiments. Like that, in holography also, we will be getting fringe patterns. So these fringe patterns, that the holograms we used to call, then the fringe patterns we used to call it as hologram, recorded at different temperatures, and we process this hologram using some different softwares, numerical reconstruction using H-digital softwares. That is, commercial available softwares are available in our laboratory. There is H-digital is an advanced image processing software we purchased, and it eliminates the requirement of laser for reconstruction of the holograms. So there are multifunctional features of these softwares for processing. So what we are getting is, from the holograms, that we can reconstruct, we can generate fringe patterns, and I think maybe it is not visible. Can you see small holes inside the fringe pattern? Anyone can give answer. Can you see small holes in the fringe pattern?
Yes, sir.
Yes. Okay. So the holographic fringes generated during heating up process. So using some mathematical tools, we can use this holograms for effective visualization. That is the effect of histogram equalization. Number of techniques are there for improving the quality of holograms. So finally, what we are getting is the hologram with definite holes. Listen here. You may misunderstand this hole is very big. No, it is not big. It is very, very small. I'm counting the number of fringes. 1, 2, 3. There is the hole, or the diameter of the hole is 3 lambda by 2. That is, one fringe represents lambda by 2. That is 3 by 2 lambda by lambda. 3 lambda by 2. There is lambda is 600 nanometer. That is 3 by 2 into 600. That is 3 into 300. That is 900 nanometers. Nearly, it is very, very, very small void or gap. So we can visualize all these holograms using low pass filters, high pass filters, and original filtering process. Okay, this is about the methods of holographic fringe pattern and analysis using holography non-destructive testing method. Like this, like this, any object of our interest can be detected whether it is containing an anomaly, any circular anomaly or a void or a breaking, a bond breaking or an inhomogeneity. Anything can be discussed and observed by using the holographic filters. So just like a doctor identifies a break, a bond breakage. So that can be identified using the X-ray. Just like an expertise in holography, non-destructive testing facility can verify whether this material is having this void or denominations. So this is about the technique of holography, non-destructive testing that we have published in recently about the holography testing. So next step is regarding speckled non-destructive testing. Let me know how much time I left or whether we need any discussions at this point of time, or which I shift to speckled to the next day with the speckled metrology. Dr. Sunir or Dr. Shine?
So, participants, you have any discussion or?
Pardon?
For the participants, dear participants, you have anything to discuss or?
Yeah. Then how much time left for me also that?
Sir, this session we can wind up around 4:30, 4:35, as you like.
Okay, so now let us discuss these so far we have discussed, okay?
Okay, sir.
Okay, it's better because the next one I'm moving to speckled non-destructive testing that I can discuss with speckled metrology, no problem. Okay, any queries on this regarding? Okay. So actually, so far I have presented about holographic non-destructive testing. So this is the research group. I think you can see my research group team, my research team. I have presented the work so far done by Dr. Radish, who took PhD with me. These are the PhD holders. So far, I have presented the work related with Dr. Radish. Okay. So, any queries regarding the formation of fringe patterns or the holographic testing can be discussed, or otherwise we will move to the next session.
Mujeeb sir, I have another question.
Please.
How can we collaborate with your project, sir?
Of course, madam. I'm happy to share and collaborate with the MES College of Engineering, with any of the departments for mechanical engineering, or so we can have some local MOUs, Memorandum of Understanding, at college level and with the International School of Photonics. Or if you want to extend the collaboration with the entire institute with the Cochin University also, I can also happy with the authorities. I can discuss with the authorities because MES is also very precious for me. MES College of Engineering is also very precious for me in my career and life. So no problem. Don't worry about the collaboration. After our FDP program, Dr. Sunish and yourself can write to me. We can collaborate, mutual research collaboration or academic collaboration. We can take part. No problem.
Okay, thank you. Thank you. Tomorrow morning session, most probably I can't attend. So
tomorrow, I think my session is at 3:30 again tomorrow evening.
Yes, sir. Your session.
Then no problem. Okay. I'll do it. I can.
Okay, so I'll be continuing the spectral metrology tomorrow. I think for holography related things, mechanical engineering department can collaborate and can do some projects, MTech project or BTech project. And here the computer science departments can also collaborate because computer programming is also we are doing. we are having some students doing with the programming, either MATLAB or MATLAB coding. No problem. Okay.
Okay, thank you. Thank you. Anyway, we will discuss this matter. Mujeeb sir, ഞാനൊരു ഗസ്റ്റിനെയും കൂടെ കാണിക്കാം.
Yes. Yes, sir. Professor Jamila was my own colleague. Okay. Yes. Very happy to see Professor Jamila. Okay, thank you.
Professor Jamila. Okay. Then Shine sir, shall we wind up?
Yes, madam.
Yes, ma'am.
Any questions from participant side?
So even otherwise you can discuss with me at the end of tomorrow's talk, no problem. Okay.
Okay.
So, dear participants, we request you to raise your queries or issues or anything you want to discuss with the professor. Please feel free to ask him, because we have an eminent here. Okay, so
this is a golden opportunity for participants.
Yes,
this is a golden opportunity for participants. Yes,
it's a golden opportunity, because Sir is over here to answer you.
Okay, no problem. They will be asking, and even you can interact with me directly through my email ID if you have specific questions on your research. If something is related with your research, tomorrow I'm planning to discuss something very interdisciplinary. Any branch of students can pursue optics research. Not only for a physicist or photonics persons, any branch can collaborate with optics research will be giving tomorrow. Okay. I hope more questions may be from participants tomorrow.
Okay, thank you.
So,
thank you.
It's my pleasure to invite Dr. Sumitra, Assistant Professor, Department of Physics, Devasam Board College, Taliwala, Harambur, to propose vote of thanks. Madam Sumitra.
Yeah, thank you, sir. So good evening, all. I hope you can hear me. So I'm honored with the privilege to propose a vote of thanks today. So Dr. Mujeeb, sir, it was a very great presentation and we thoroughly enjoyed it. So I used to be skeptical about senior professors giving lectures, because I used to believe that everything is about to go over my head. But the series was like, this class was very thorough about the basics. And I believe that's the reason why there are no many doubts, because it was really thorough and we really enjoyed it. So we're looking forward for your talk tomorrow also. And I would like to take this opportunity to acknowledge the contribution of all those who really worked hard to make this FDP possible. So once again, on behalf of all the participants, I thank Dr. Mujeeb sir for this amazing lecture, and also all the coordinators. Thank you.
Thank you, Sumitra. Okay.
So today we can wind up the session. So tomorrow be at 10 o'clock, 10:30.
Okay, thank you. Okay.
Mujeeb sir, one second. Mujeeb sir, ഞാൻ ബ്ലൂടൂത്ത് ഒന്ന് ഓഫ് ചെയ്യാം.
Yes, please. Okay.
കേൾക്കാം.
കേൾക്കാം. മോൻ MBBS കഴിഞ്ഞോ? ഇല്ലല്ലോ.
സെക്കൻഡ് ഇയർ കഴിഞ്ഞു.
സെക്കൻഡ് ഇയർ ആയിട്ടുള്ളൂ. വെരി ഗുഡ്. ഓക്കെ. രണ്ടാമത്തെ ആള്, അടുത്ത ആള്
പിന്നെ +1.
ഓക്കെ. അപ്പൊ +1 തുടങ്ങിയില്ലേ ഇപ്പൊ?
അല്ല, കേരളയിൽ ജോയിൻ ചെയ്യാനോ. അതുകൊണ്ട് ഇനി അടുത്ത ആഴ്ച ഇന്ന് അലോട്ട്മെന്റ് വരുമല്ലോ.
അതെ, +1 കേരള എന്ന് പറഞ്ഞാൽ മനസ്സിലായില്ല.
സ്റ്റേറ്റ് സിലബസ്.
സ്റ്റേറ്റ് സിലബസ്. ഓക്കെ. ശരി.
ഞാൻ
ബ്രേക്ക് ചെയ്ത് പോകുന്നു.
കഴിയട്ടെ പ്രോഗ്രാം.
യെസ്. ഓക്കെ.
മോളും ഒക്കെ
മോൻ ബിടെക് കഴിഞ്ഞ് അങ്ങനെ നിൽക്കുന്നു.
മോള് +1. CBSE. സാഹിറ സുഖമായിരിക്കുന്നു?
അതെ സുഖമാണ്. അപ്പൊ ട്രിവാൻഡ്രം മെഡിക്കൽ കോളേജ് തന്നെ.
അന്വേഷണം പറയണം എല്ലാരോടും.
ഓക്കെ, താങ്ക് യു. അതായത് നിങ്ങൾ എല്ലാവരും കണ്ടതിൽ സന്തോഷം. MES കോളേജിന്റെ ഭാഗമാക്കാൻ കഴിഞ്ഞതിന് വീണ്ടും ഒരു സന്തോഷം. എനിക്ക് തോന്നുന്നു ആദ്യത്തെ കുറച്ച് സ്ലൈഡ് കുറച്ച് ആദ്യം അത് സ്ലൈഡ് മൂവ് ചെയ്തില്ല എന്ന് തോന്നുന്നു.
അതെന്താന്നറിയോ, എനിക്ക് തോന്നുന്നത് സ്ലൈഡ് ഷെയറിംഗ് കൊടുക്കാഞ്ഞിട്ടാ. മുജീബ് പറയുന്നുണ്ട്, പക്ഷെ സ്ലൈഡ്സ് മാത്രം മൂവ് ചെയ്യുന്നില്ല.
അത് ഞാൻ കൊച്ചിൻ യൂണിവേഴ്സിറ്റിയെ കുറിച്ചുള്ള ഒരു ബ്രീഫ് ഡിസ്ക്രിപ്ഷൻ ഉണ്ടാക്കിയിരുന്നു എല്ലാവർക്കും വേണ്ടി.
അല്ല, അതന്നേരം ഞാൻ വിചാരിച്ചു അതുകൊണ്ടാണ് അത് മൂവ് ചെയ്യാത്തതെന്ന്. പക്ഷെ അതുകൊണ്ട് ഞാനും ശ്രദ്ധിച്ചത് അല്ലാന്ന്.
ഓക്കെ, ഇപ്പൊ പിന്നീടുള്ളതൊക്കെ മാറിയല്ലോ ലാസ്റ്റിലൊക്കെ.
മാറി.
ശരി. സൽമയൊക്കെ സുഖമായിരിക്കുന്നല്ലോ?
സൽമ അണ്ടർ പ്രിപ്പറേഷൻ ആണ്. MD ഒക്കെ എന്തെങ്കിലും ഒന്ന് എഴുതിയെടുക്കണമെന്ന് പറഞ്ഞപ്പോ എന്റെ കൂടെ ഉണ്ട്.
ശരി. സാറയോ?
സാറ ഇപ്പോ +2 കഴിഞ്ഞു, റിപ്പീറ്റ് ചെയ്യാമെന്ന് തീരുമാനിച്ച് നിൽക്കുന്നു.
ശരി. സാറും സുഖമായിരിക്കുന്നല്ലോ?
സാറിപ്പോ KDISCന്റെ പ്രൊജക്ട് ഓഫീസറായിട്ട്, സ്റ്റേറ്റ് ലെവൽ പ്രൊജക്ട് ഓഫീസറായിട്ട് ജോയിൻ ചെയ്തു.
വെരി ഗുഡ്. വിശ്രമമില്ല, ഇനിയും വിശ്രമമില്ല അടുത്ത 4 വർഷം.
വിശ്രമം എടുത്ത് വീട്ടിൽ വന്നിരുന്നതാണ്. അപ്പൊ അവര് വിടുന്നില്ല. നോളജ് എക്കണോമി മിഷൻ അവര് വിളിച്ചു. അപ്പൊ പിന്നെ അതുമായിട്ട് അസോസിയേറ്റ് ചെയ്ത് പോയി. 1.5 മാസം 2 മാസമൊക്കെ ശമ്പളം ഇല്ലാതെ.
മാഡം വൺ സെക്കൻഡ്, ഞാൻ ഈ റെക്കോർഡിംഗ് ഒന്ന് ഓഫ് ആക്കിട്ടെ. ഇത് റെക്കോർഡിംഗ്
ഡോക്ടർ സുനീഷ് അത് എഡിറ്റ് ചെയ്യുമ്പോ പിന്നെ അത് കളയണം കേട്ടോ.
കളയാം.